Welcome to the last of the basically the solution lectures before we get into rate law. Now, rate law is an analysis of what energy is needed for a completion of a reaction, or what energy is produced by the reaction itself. Today we're going to do a lot of definitions. You may want to get out your magnifying full screen capabilities that all you folks seem to be quite conversant at doing. I think it's pretty clear, so it shouldn't be too difficult for you. We start out as the properties of solutions. Now, molarity and molality and percentage by mass are all things that are used in chemistry and used fairly commonly. Molarity is the one we've covered already. It's moles per liter. Molality is used in industry for the obvious reason. First, you can determine the number of moles by mass, and you can determine the solution mass directly also. So molality is used a lot in industry because that's moles of solute dissolved in kilograms of solution. And molality is the one that's widely used in industry because you can measure volume reasonably accurately, but mass you can measure readily to the nearest 10,000th of a gram without much hassle, and reproduce it quite accurately. The mole fraction is the number of moles of A divided by the number of moles of A plus the number of moles of B, just like every fraction you've ever done all of your life. I wrote this high and large, likes dissolve like. Mostly that's used for polar compounds. Polar compounds can dissolve polar compounds and non-polars cannot. And you're going to get into quite a bit of that as we get further along in the course. Hydrophobic means fear of water, if you want. In chemistry, it means it will not dissolve in water. And hydrophilic means it will. So again, these are terms you need to learn. Normality refers to ions primarily, mostly hydroxide and hydrogen ions. The normality is the equivalence per liter of the hydrogen ions or the hydroxide ions, whichever one is you're utilizing for that particular reaction. Mass percentage, implied earlier, is the mass of the solute divided by the mass of the solution times 100. That's the way you get every percentage. Okay. Next on the agenda is energy or heat, often referred to as delta H. And you're going to hear a lot about delta H for the next several sections in this course. The delta H of a solution is always the addition of all of the components. Delta H1 plus delta H2, et cetera, et cetera, et cetera. This is called the enthalpy of solution. Delta H is differences between this is a dissolving delta H. It would be the differences between the molecular attraction of the crystalline material or the dissolving material, the material won't dissolve, and the disruptive characteristics of water. And those differences would give you the delta H needed for the solution that you want. Now we skip to gases. Pressure affects gas most because of logic. Pressure affects gas because there's more space between the molecules of the particulates or whatever kind of gas you're dealing with. Henry is the guy that came up with the law, and it's called Henry's Law. It's not any more complicated than that. Now, Raoult, he got a little more technical. He said that vapor pressure is discernible by understanding the mole fraction of the components involved in the dissolution. And his law states that the pressure of the solution is equal to the mole fraction of the solvent times the pressure of the solvent. Again, I've got to find the X is the mole fraction and P is the pressure of the pure solvent. Now, Raoult's law really holds true for most dissolutions, except that hydrogen bonding messes up the predictability of this. And the reason for that, of course, is the polarity. The good thing about it is it only applies to those that are affected by the hydrogen bonding the most, which is nitrogen and oxygen compounds. So you only have to make that adjustment under those circumstances. Next, we go to the change in temperature. And the change in temperature is equal to kV times the molality of the solution. K, of course, is the Kelvin temperature, and B is the boiling. So kV would be the Kelvin boiling temperature. Colligative properties is another term that's widely used. It talks about the characteristics of substances that are dissolved and how they're dissolved and what energy they're dissolved at and what state they dissolve the best. These are all called colligative properties. Now back to delta T. The lower the temperature shifts when equilibrium shifts. I beg your pardon. The lower the change in temperature shifts when equilibrium shifts, it's called an endothermic process. Thus, a solid plus a liquid forming a solution is produces energy. Now, to be an endothermic process, energy has to be used to form it. But if you put a solid in a liquid, most of the time it'll change the temperature. And that's called an exothermic. Exo means going out. And there's lots of ways of measuring that, and you're going to learn a whole much more than you really want to know as we get into rate law, which is the next aspect of this course. And back down to the next example. You're dissolving a gas in a liquid, and it produces a solution at equilibrium. The delta H of the solution is less than 0, which means it took energy in order to dissolve it. And this is called an endothermic reaction. Okay, we already talked about moles and molarity and all that kind of stuff. Osmotic pressure, which I kind of talked about it fleetingly earlier, is symbolized by the pi, which you learned in geometry or trigonometry or algebra, depending on what course you took. The symbol pi is equal to MRT. M, of course, is the grams of solute dissolved, grams of solute per molality. And R is universal gas constant. And T, again, when you see a capital T, it almost exclusively refers to temperature in Kelvin, which is the centigrade degree plus 273.16. Supersaturated. Now, we actually used to do this, and it's kind of fun. You dissolve sugar as much as you can get it to dissolve, and then cool it really slowly, very slowly. And you can look at the surface of it, and the doggone surface of it looks like it's almost solid. And then you take one sugar crystal and drop it into the solution. At that juncture, you get gobs of sugar settled out. And that's when you have a supersaturated solution, where it is actually dissolved more than it's technically capable of doing by that particular temperature. And that's supersaturated. Okay, back to the pressure relationships. Pressure on a solution is always a capital C. Let's see if I can look at myself here. K is the constant involved. There's always constant involved in your pressure relationships. It's generally individual of a particular substance involved. And the PG is the partial pressure of the gas. So this is a gas relationship, which most of these are. And then if you do a little mathematical manipulation, you solve for K, which is generally what you want to find is what is the constant for a particular substance. And you'll often note, have available the other materials and solve for K. Now, I decided to do a pressure problem. And what this does is it tells you what temperature occurs when you dissolve a couple of substances. And in this case, we're dissolving C2H6O2, 50 milliliters of it in 50 milliliters of water. And the question asks, what is the molality of this? Now, there are some constants that you probably should write down on your cards again. Water's boiling constant is 0.52 degrees centigrade per molal. And the freezing point constant is 1.86 degrees Celsius per molal. So using those as the standards, we can work the problem out. The change in temperature for the boiling is equal to the constant of the boiling times the molality. The change in temperature of the freezing is the same thing, only it's the constant freezing times the molality. Now, there's some stuff given in the problem here, which you can calculate. First, the density of the solution, which is given up here, is 1.12 grams per cubic centimeter. Well, it was also given to you that you got 50 cubic centimeters of it. So if you multiply 50 times 1.12, cubic centimeters cancel out, and you're left with the number of grams, which is 56 grams. Now, if you divide it by the molecular weight, in other words, you add up 2 carbons and 6 hydrogens and 2 oxygens, you get 62.04 grams per mole. Divide those two out, and it gives you the mole fraction of 0.903. And then the 0.05 kilograms refers to the 50 grams of water that you dissolve the C2H6O2 in. And you change it from 50 grams of water to 0.05 kilograms. Because again, this is a kilogram relationship. And that comes out to be 18.1, and that's grams per kilogram. No, that's a mole fraction. That's moles per kilogram. And then you multiply that by the constant for the boiling point, which is over here, and you come out with 33.7 degrees centigrade change, which means it's reduced negative 33.7 degrees centigrade. Now, these are just classic problems. They're not particularly difficult if you know what you're looking for. And generally what was said in the beginning is, what is the molality? And you solve for the molality, and then you find what is the amount of change temperature-wise. Solve for that. And I'm on a problem kick, so I said, wait a minute, what if you've got phosphoric acid, H3PO4, and you react it with sodium hydroxide? Well, you know, by now you should have that if you add an acid and a base, you're going to get a salt and water. In this case, it's sodium phosphate plus water. And the question asked, if you got 2.74 moles of sodium phosphate formed, what is the amount of phosphoric acid you started with? Well, again, purposefully, I didn't balance the darn thing because I want to remind you guys periodically that you got to balance equations if you're going to make this work. Now, it balances out pretty slick by inspection. You got sodium phosphate on this side. You got 3 of them, and you put a 3 over here in front of the sodium hydroxide, and now you got 3 sodiums and 3 sodiums. You got 1 phosphate, 1 phosphate. You got 3 hydrogens and 3 hydroxides, which of course gives you 3 waters. So over here, you just put a 3 in front of the water and you're balanced. Now, how does that help you? Well, if you know you got 2.74 moles of sodium phosphate formed, and you know that you're using 1 mole of phosphoric acid to produce 1 mole of sodium phosphate, and the equation is balanced, then it's pretty straightforward. You would use 2.74 moles of phosphoric acid to produce 2.74 moles of sodium phosphate. I made it easy so you can understand it readily. All right, second question is, you got 2.75 tons of copper sulfate, and you oxidize it, which means basically you superheat it and spray a stream of oxygen, probably bubble it through, superheated, and then you get your nice copper metal out of it, and sulfur dioxide, poisonous gas, is a product. First thing you do is check and see if it's balanced, and you can see by inspection it's balanced. So if your relationship is 2.75 tons of copper sulfide, you would take the mass of the copper and sulfur, divide it, and I'll give you the number of moles, and then on the other side of the fence, you know, it's a 1-to-1 mole-to-mole relationship, so you look up the number of moles uh, by looking copper and sulfur up on the periodic table. That gives you the mass. You divide that into 2,750, since this is metric tons, would say kilograms. And that'll give you your number of moles. And then on the other side, it's the same number of moles, but this time you have a different multiplier because copper, I don't remember what it weighs, but you can look it up easily enough. And that'll give you the number of tons, actually the number of thousands of kilograms, and you divide it by 1,000, it gives you tons, if you wish, of copper metal produced. This is one of the, if you got a high sulfur copper ore, this is the way they actually produce copper metal, molten. All right, next question. You have 50 milliliters. Now this is where you got your mole fraction that we talked about earlier. You got 50 milliliters of toluene, which is a poisonous organic liquid, and you're pouring it into 125 milliliters of benzene, which is another poisonous organic liquid. The idea is to find out what is the mole fraction of this. Now, to do that, you got to go back to logic here. 50 milliliters of toluene times the grams per milliliter. In other words, you'd find the molecular formula of toluene, add it up, grams per milliliter, multiply it by grams per, first you'd find it grams per liter and then change it to grams per milliliter. And then you'd cancel out your milliliters and it'd give you the number of grams. And it'd be 43.4 grams of the toluene. And you do the same thing with the benzene. It's 125 milliliters, and it's 0.874 grams per milliliter, and that gives you 109 grams of the benzene. So the percent of the toluene would be straightforward. It's 43.4 divided by 43.4 plus the benzene, which is 109, and it gives you 25.5%. Straight up, easily done. Over on the other side of the fence, you would take your 43.5 grams of toluene, and the total solution is 125 plus 50, which is 175 milliliters of the solution, times 1,000 because we change everything to liters, and multiply it by the moles per or grams per mole, divided by the grams per mole for the toluene, which is 92.13. And it comes out to be 2.69 moles per liter for that solution. And that works out quite straightforwardly. You do the other thing the same way with the benzene. 109 grams of the benzene times 1 over 7811, which is what the molecular weight of the benzene is. And that gives you 1.40 moles. And back up here, I skipped a little bit on the toluene. You got 43.4 grams of toluene divided by 92.13, which is the molecular weight of the toluene. It gives you 0.47 moles of the toluene. So you put the 0.47 moles of the toluene divided by 0.471 moles of toluene plus the benzene, which is 1.4 moles, and that gives you the mole fraction of 0.252. Again, these are not impossible questions at all if first you understand what's given, or what you can look up easily, and what you want for an answer. Again, you need to have gone through this stuff as we go through and develop a fairly workable understanding And again, I told you quite some time ago to buy yourself an old used textbook. 20, 25-year-old textbooks are the best. And do some of the problems. Very often they'll give you the answers to at least some of the problems in the back of the book. Do some problems and become familiar with it. You have to do a little road work for every one of these lectures. It's not like uh, I'm giving you one continuous lecture and all you got to do is write down the answers. Uh, you have to build on this. And that's the reason I'm doing this as a survey course rather than a technically difficult course. Now, some of this is a bit technically difficult, but overall, I'm just scratching the surface as far as a real in-depth 3-semester course in general chemistry. This basically would be a 1.5 semester, um, about a 1.5 semester survey course in today's college chemistry. And I'm not giving away any secrets, but college chemistry is not as tough today as it was back when I did it. I mean, it was considerably more difficult. And the courses I taught at all levels were considerably difficult than what they teach in college chemistry for a general survey course. So this is kind of in between. This is more complete, I think. That's the reason I'm doing it the way I'm doing it. So hopefully you blow the page up so you can see everything nice and clear. I've written it where it's as legible as I write. And look up to the section in your textbook that you bought that deals with properties of solutions and colligative properties, and you'll bump into all this stuff. I just tried to give you an overview of it. So give it a go. Next thing is rate law. So strap on your boots. It's going to be tough.